Congruences in Z. This is what we are going to learn in this video. So we will start with section 2.1 from Hungerford's book, and this section is about congruences and congruence classes. Okay, fix an integer n, a positive integer n. So fix it. Say for example, I will fix n to be 5. Okay, we will say that two integers a and b are congruent modulo n whenever n divides the difference between them, whenever n divides a minus b. So in particular here we will say a is equivalent to n modulo b, or a is congruent to b modulo n. A is congruent to b modulo n, and this happens whenever n divides a minus b. So if we fix n equals 5 here, then we will find that 7 is congruent to 2 modulo 5. Actually, I have here more examples that are ready. Let's look at them a little quick. So 14 is equivalent to 2 modulo 3. That's because 3 divides 14 minus 2. 10 is equivalent to 1 modulo 3 because 3 divides 9, and so on. 13 is equivalent to negative 1 modulo. So we need to fix that. I meant this to be 14. Sorry. 14 is equivalent to negative 1 modulo 3, since 14 minus negative 1 is divisible by 3. Negative 8 is congruent to 4 modulo 3. That's because negative 8 minus 4 is negative 12, and it is divisible by 3. And so on. Negative 8 is congruent to negative 14 modulo 6. And here notice that we have 10 congruent to 1 modulo 3 and 1 congruent to 10. And that means we have here symmetry, and we will see it. And these are other examples that you may look at. Okay. Let's see what we have next. Okay, good. So congruences enjoys the same properties that integer number do. So every element is congruent to itself. So again, we are fixing n. We assuming n is fixed. Okay. Now every integer is congruent to itself. So this property we call it reflexive. Now if a is congruent to b, then b is congruent to a modulo n, and we call this symmetric. Here, if a is congruent to b modulo n and b congruent to c, then a congruent to c, and this is called the transitive. Okay, so let us prove these things. To prove part A, it's direct, since n divides 0, so n divides a minus a, so this gives a is congruent to itself. Okay, now here, if a is congruent to b, that means n divides a minus b. Therefore, thus, n divides b minus a, and hence b is equivalent to a modulo n. Part 3. If a is congruent to b modulo n, that means n divides a minus b, which means a minus b is a multiple of n. So it equals n times k for some k in z. For n to divide a minus b, it means a minus b is a multiple of n. Same thing here. P is congruent to c modulo n. That means b minus c is a multiple of n, which equals n times t for some t. Now we go here. A minus c, we will write it the following way. We will subtract b and add b, so we change nothing. Now this part, a minus b is nk, b minus c is nt, so we get a minus c is a multiple of n, which means n divides a minus c, and which implies a is congruent to c modulo n. Okay, let us see another theorem. Let me rewrite this theorem. It says if we have a congruent to b modulo n and c congruent to d modulo n, then what we have here, like let me write it here. And if we have integers, if we have a equals b, c equals d, then add, we will have a plus c equals b plus d, correct? And if we multiply, we get ab equals, sorry, ac, I mean, ac, multiply these two things, integers, and then these two integers, we will get an equality, which means equals bd. So same thing applies here. This is analog to 1 and this is analog to 2. Okay, so we go back and write here. Now if we add these two things, a plus c will be the same as if we add these two things, b plus d. But the same here for us means they are congruent modulo n. Same thing if we multiply, a times c is congruent to b times d modulo n. So now we got the picture of what this theorem says. So let us prove it. Now since we have a is congruent to b modulo n, then a minus b is a multiple of n, so it is n times k. Same thing here. C minus d is n times t for some k and t integers. Now, we want to prove this part, which means we want to see what happens for a minus a plus c minus b plus d. And we hope this is a multiple of n, because if this happens, then we get the congruence. So reorder the numbers. We can do that. So we get a minus b, c minus d, but a minus b is nk, c minus d is nt. Take n as a common factor. Then we got this as a multiple of n, which means n divides their difference. And then we got this true. And then we proved part 1. Now to prove part 2, what is part 2? Let me write it here. We want to show that a times c is congruent to b times d modulo n. So we hope that a c minus bd is a multiple of n. So let's see what we do here. We subtract it. This is a trick. We subtract bc and add bc, so we change nothing. Now, do simplification. Take c as a common factor, then we get this, and d here as a common factor. So in particular, I mean this thing here is that, and this thing here is that. Okay? Now arrange things. Now we know that b minus c, we have seen it before, it is nk, and c minus d is nt. Now collect things together, take n as a common factor. Now we got AC minus BD is a multiple of N, which means N divides AC minus BD, and therefore AC and BD are congruent modulo N, and the theorem is proved. Okay, next, before we go to the theorem that comes after, I want you to consider the following notation. Okay, this is an interesting notation that we need to see. Okay, notation. Oops, okay. Okay, what this notation says, in here it says fix an integer n, as usual. Fix an integer n. Now consider what we have here. N times k. Sorry, n times z. Now z is the set of all integers, 0 and the positive integers and the negative integers. What we do here, we will multiply n with all the integers. So I will multiply n with k, where k is any integer, where k takes all the values of z. Okay, now to see that happening, look at 3 here. So we will multiply 3 with all the integers. Now this is 3 times 0, 3 times 1, 3 times 2, 3 times 3, times 4, times 5, and so on. 3 times negative 1, 3 times negative 2, 3 times negative 3, and so on. Good? Okay. Another notation, if I choose an integer a, and then add a to nz, the one I already got, which means I will add the integer a to every number inside nz, to every number inside nz. But any number from inside nz is of this form. So I will add a plus n k. N is fixed, a is fixed, but k runs over all the integers, positive and negative. And to see that, let's go to this example here. So we have a 3z already. So 1 plus 3z, what we do, we will add 1 to every element in 3z. Correct? So we have 3z already up here. So we will say 1 plus is 0, we get 1. 1 plus 3, we get 4. 1 plus 6, we get 7. 1 plus 9, we get 10. 1 plus negative 3, we get negative 2. 1 plus negative 6, we get negative 5, and so on. Same thing, 2 plus 3z. Okay? Now, I wanted to present more examples so that you have the feel of this notation. Now 5z here means we will multiply 5 with all integers. So multiply 5 with 0, with 1, with 2, with 3, with 4, with negative 1 and negative 2. Now here we say 3 plus 5z. So I will add 3 to this to get 3. Add 3 to this. So I need to fix that. So we will get 8. And then add 3 to 10. We get 13, and so on. Notice here something interesting, that if we start at some integer and then move to the right, and then we will find ourselves adding 5s. So we adding multiples of 5s. Move to the left, we are taking multiples of 5. Why this is happening? Because we multiplied z by 5. Now, same thing happened here. If we start at 3 and keep moving, then we'll find that we add 5 at every time. And here we subtract 5. Same thing happened with the 3z. We move here, so we add 3's, copies of 3's, or move to the left, and then you are subtracting copies of 3's. One more example is 6z. So 6 times 0 is 0, 6 times 1, 6 times 2 times 3 times negative 1 times negative 2. And again, if we start at any number, then we move to the right, we will find ourselves adding copies of 6. Moving to the left, we will find that we are subtracting copies of 6. Here we add 3 to every integer here, so add 3 we get 3, add 3 we get 9, 15 and 16. And I hope you have the feel of this notation now. Why do we need it? How this is related to equivalence classes? It is related somehow the following way. Okay. Now, I will explain what this definition means. I will start here. Assume B is congruent to A. So we have N fixed, A fixed, and B is congruent to A. That means N divides B minus A, which means B minus A is a multiple of N times K, for K can be any integer. It can run over any integer. And this means from here to here we get B equals A plus NK. So if B is congruent to A, then we get B equals A plus NK. Now, if we go here, the equivalence class of A, what do we mean by the equivalence class? This is what we are, the congruence class of A modulo N. This is what we are defining. The congruence class, it is here. The congruence class of A modulo N is the set of all integers. So again, we are fixing N and taking an A and fixing it. Good? Now I am asking, bring to me all the elements, all the integers that are congruent to A modulo N. Collect all the integers that are congruent to A modulo N. So this is the way we are doing it. We will call all integers P such that B is congruent to A. But above here, we have seen such an element takes that form A plus A and K. But with the notation above, we know that means it is A plus NZ. So the equivalence class of A modulo N takes this form, A plus NZ. And actually, if you go back here, this will be the equivalence class of 3 modulo 6. And this is the equivalence class of 3 modulo 5. And this is the equivalence class of 2 modulo what? Modulo 3. And this is the equivalence class of 1 modulo 3. So it is the equivalence class. Okay, now let's go back down to the definition of the equivalence class and see more examples. Now these examples have something interesting to tell. Now we will take the equivalence class of 2, but modulo different numbers. So at the beginning here we're taking the equivalence class of 2 modulo 3, which is 2 plus 3z. Compute that as we done above, you will get this set. Now the equivalence class of 2 modulo 5z. So it is 2 plus 5z. Compute it and you will get it that way. Now the equivalence class of 2 modulo 6 and compute it, you will get this set. Now look here, this is equivalence class of 2, equivalence class of 2, equivalence class of 2. But with respect to some different modulo at each time. This gives different sets. This set is different than this and different than this. What I want to say here, the congruence class of 2 modulo 3 has nothing to do with the congruence class of 2 modulo 5. And also it has nothing to do with the congruence class of 2 modulo 6, and so on. These are different environments. Modulo 3, modulo 2, modulo 5, modulo 6, modulo 4, modulo any number. At every time of such cases, we live in a different system, in a different environment. So we cannot compare the equivalence class of 2 modulo some number to the equivalence class of 2 modulo some other number. We cannot compare it. There is no relation between them. Okay. Now let's see something here really interesting. And I made pictures so that they speak for themselves. What do I mean here? Look, we will conclude this theorem and this theorem and this theorem from this line. Let us see what that says. In this theorem here, it says if A and C are congruent modulo n, if they are congruent modulo n, then they give the same equivalence class. This is important statement. This is an important statement. Okay. And this says if we have two congruent classes, if we get two congruent classes, then they are either disjoint, which means they share nothing, their intersection is phi, or they are the same, they are identical. Okay. Let us see here. We'll come back to theorem 2.3. Now, in here, this gives all, let me take that. This gives all the equivalence classes modulo 6. So for this line, we are working modulo 6. So the equivalence class of 6 is 6, 12, 18, 0, 24, minus 6, minus 12, minus 18, minus 24. This is the equivalence class of 6, which is here. And it is the same as the equivalence class of 0. So we are saying it is the equivalence class of 6, equivalence class of 0, or equivalence class of any number inside here. So now pay attention. Take any of these numbers. Say we will go to negative 6 here. And take the equivalence class of negative 6, which means you move by multiple of 6 because we are working here. Let me write it. And here we have it to be 6. So we are working modulo 6. So if I start at any number such as negative 6 and take the equivalence class of it modulo 6, then I will jump by multiples of 6. Okay. To make it clear, let me move to the class of red numbers. The equivalence class of 1. Here we go. So this is 1. They have red color, and 7, and 13, and 19, 25, negative 1. All of these numbers are congruent modulo 6. Do you agree? Because the distance between any two of them is a multiple of 6. So the distance between any two of them is a multiple of 6. That means any two of them are congruent modulo 6. Good. Now, same thing I will say here. It is the same as congruence class of 5. Start here at 5 and jump by multiple of 6. You will find yourself in the same set. Or if you start at 7 here and then jump multiples of 6, then you will find yourself still in the same set which has a red color. So the equivalence class of 1 and of negative 5 and of 7 and 13, 19 It's always the same equivalence class. Here I am saying if you take any two elements from this congruence class, then I mean the congruence classes of any two elements from inside here is the same, which is this set, this congruence class, the red one. I will just repeat the same thing for the blue now. Okay, the equivalence class of 2, here is 2, is congruent to 8, it's congruent to 14, congruent to 20, and to -4, -10. Why all of these numbers are congruent? Because the distance between any two of them is a multiple of 6. And it is the same class of 2 is here, the same class of congruous class of 4, and same congruous class of -20, 22, -16 at 8, 14. Take, for example, go to 14 and move by jumps of multiples of 6, then you will find yourself moving on the same set that has a blue color. We repeat the same process for the green equivalence class of 3. Jump by 6, jump by a multiple of 6, then we will find ourselves in this equivalence class, which is the green, which is the same as the equivalence class of any number inside here. And now you get the idea, equivalence class of 4 and equivalence class of 5. Good? So I hope this picture and these equivalence classes gives you help you to visualize the idea in here. And before I move, I will write, because we are working with n equals 6, I will just steal some notation. I will say we will write z sub 6 to be the set that consists of all of these congruent classes. So okay, I do this. So the set that consists of all the congruous classes modulo 6. The set that consists of all congruous classes modulo 6. So I think now you see it. Okay. Okay, good. Now let me go back to theorem 2.5. It says if a is an integer, and r is the remainder of what? If we divide a by n, I mean here, divide a by n, a divided by n gives a result q and a remainder r. Now this theorem says here the equivalence class of a and of r, they are the same. They give the same equivalence class. Let us do some try. Let us pick a number, divide it by 6, which is our n, and take the remainder. And then compare the equivalence class with the number we started with and the equivalence class with the remainder. Okay, let us choose some number. Let us choose 19. Okay, let's go to 19. Okay, divide 19 by 6. So we get 19 equals 3 times 6 plus 1. So this is r. This is a. And this is n. Now this is r and this is a. Is it true that the equivalence class of 19 is the same as the equivalence class of 1? Let us see. If they have the same color, then this is true. Equivalence class of 19. And here is 1. Okay, good. So equivalence class of 1 and 19. It is the red one. Good. So the number and its remainder after dividing by n, they live in the same equivalence class. They have the same equivalence class. Okay. Now we got a good visualization of the three theorems, and now we go to prove them. Proving them is just some technical work. So let's go for it. Now this theorem here says if A is congruent to C modulo n, A congruent to C modulo n, if and only if their equivalence classes are equal. I rewrote this in red. A is congruent to C modulo n, so their equivalence classes are equal. Actually, in abstract algebra in general, to understand things, to comprehend them and feel comfortable to them, you need to put them in some statement that consists of words. I will do this for theorem 2.3. I will say two elements have the same equivalence class if they are congruent. I will say it again. Two elements will have the same congruent class modulo n if they are congruent modulo n, if and only if. Okay? I will say it one more time but differently. Two elements live in the same congruent class modulo n if they are congruent modulo n. Okay, so now let's go and prove it. We will prove this direction, which means we assume A equals C modulo n, and we want the equivalence class of A to be the equivalence class to equal the equivalence class of C. So it means we will show equivalence class of A is contained in equivalence class of C, and conversely, equivalence class of C is contained in the equivalence class of A. So how we do that? We choose an element in the equivalence class of A, and since it is in the equivalence class of A, that means it is congruent to A. Now we got B congruent to A and A congruent to C, so we use transitivity, and this gives B congruent to C, and that means B lives in the equivalence class of A. Now Now we chose B to live in the equivalence class of A, and we showed that it lives in the equivalence class of C, so we achieved this containment. Now do the opposite, read it by yourself, and then this containment will be achieved. Now this and this will make us conclude that the equivalence classes are equal. Now conversely, assume the equivalence classes are equal. Now A belongs to its own equivalence class because of the reflexivity. A is congruent to itself modulo n. So A belongs to the equivalence class of A. But we are assuming that the equivalence class of A is equal to the equivalence class of C as sets. So that means A belongs to the equivalence class of C. But what makes it belong to there? Because it is congruent. What does it mean to belong to there? It means it is congruent. A belongs to the equivalence class of C. That means A is congruent to C modulo n, and then we achieved this direction, and the theorem is proved. Okay, let us prove the theorem after that. Okay, now this theorem says if we have two different two congruence classes modulo n, then they are either disjoint or they are identical. Now I call them equivalence class of A, one of them equivalence class of A and the other equivalent class of C. So the theorem says they are either disjoint or are equivalent. Okay, here they are either equivalent, identical, equal. So they are either equal or they have nothing in common. They are disjoint. So let us prove that. Now, if we find them disjoint, the intersection is phi, then done. Then we do nothing. Then we achieved it. Okay. Suppose this is not true. Suppose this is not achieved, which means their intersection is not empty. And because their intersection is not empty, that means we have an integer that belongs to their intersection, which means that integer belongs to each one of them. But having P belongs to the equivalence class of A means that B is congruent to A, and having P belongs to the equivalence class of C means that B is congruent to C. Now use symmetry here, so we get C is congruent to B, B is congruent to A, so A is congruent to C. They are congruent to each other, and thus they have the same equivalence class. We just said that statement. If two elements are congruent, then they have the same equivalence class. So good. What assumed here, we assumed that they are not disjoint, and we prove then they are equal. Good. Okay. Now to prove the last theorem, we said a little while ago, if we have an integer and divide it by n with a result q, but remainder r. Now this remainder is less than the divisor, less than n. Now we write it here again, so it is here. So that means a minus r is a multiple of n. Okay, which means a and r are equivalent modulo n. So, and since they are equivalent modulo n, then they have the same equivalence class. They are equivalent modulo n, and then they have the same equivalence class. Okay, let's prove the other parts. It says that there are exactly n distinct congruence classes, which are 0, congruence class of 0, congruence class of 1, congruence class of 2, and so on. How do we know that? Okay, now we will assume that we are given a equivalence class represented by A is any equivalence class. Okay, now then this equivalence class must be one of these. Why? Because of part A, because of part 1 here, because of that. Give me an A, okay, its equivalence class here will be the same as the equivalence class of its remainder. But the remainder is one of these elements. The remainder is one of these elements. R has to be either 0 or 1 or 2 all the way to n minus 1, and we stop because it is a remainder. This is we just said that here, right? Now if you give me equivalence class for some A, I will take that A, divide it by n, and get the remainder. The equivalence class of this remainder is the same as the equivalence class of A. So an equivalence class must be one of these. One of these here. Good. Now how we prove these equivalence classes are distinct? Now if we choose S and T to be any distinct integers from this set, okay, we may assume one of them is less than the other, assume S is less than T, then their subtraction is less than n, because each one of them is less than n. So their subtraction is less than n. So n cannot divide an integer which is less than it is. So n will not divide t minus s. So t and s will not be equivalent modulo n. So their equivalence classes will not be equal. So what happened here? We chose two distinct integers, and we showed that their equivalence classes are not the same. Okay, and this proves the theorem. Now, one last thing here is notation. I have already done that. This is hard to see, but it says, it talks about the congruence, all congruence classes modulo n, or congruence classes, all congruence classes modulo n. We denote them this way, and this all equivalence classes modulo 6, we have already seen it. All equivalence classes modulo 5, all equivalence classes modulo 4, and modulo 3. So these are notation. Actually, such a set will be very important for us later, because we will study groups and rings, and this is a group and it is a ring. We will see this notation, so you need to understand what these things means, and we will do computations and we will need that many times ahead. Okay, and this is it. Thank you.